Hi all. In this video, we'll be talking about the blending problem. This is one of the LP in operations examples, and it's a very common sort of example. So this is the kind of things that they would do, that companies would, this is the kind of situation where companies would use linear programming to figure out, say, how to make trail mix or mix nut mixes and things like that. So here's a example. It's called blending. So Ferdinand Feed Company receives 4 raw grains from which it blends dry pet food. The pet food advertises 8-ounce packets each, and these packets meet the minimum daily requirements of vitamin C, protein, and iron, which are 6 units of vitamin C, 5 units of protein, and 5 units of iron. That's the minimum that is required. The cost of each raw grain is given here. So 1 pound of grain 1 costs 75 cents. 1 pound of grain 2 is 90 cents, 80 cents, and 70 cents for 2, 3, and 4. Now, each of these grains has different amounts of vitamin C, protein, and iron. So, with the constraints that you need at least 6 units of vitamin C, 5 units of protein, and 5 units of iron in the 8-ounce mixture, how should you mix the different grains together? Because you cannot directly get vitamin C, protein, or iron. You have to get them through the grains. So once you know how much of each grain you mix together, you can figure out how much of vitamin C you have, how much of protein and iron you have in total. And so that's the problem. So we have to figure this out, that we create these packets at minimum cost, right? And they meet the minimum daily requirements. Okay. Again, let me open up a PowerPoint file. Okay, so let's begin with step 1, as always. So in this case, like I explained, the decision variables are actually pretty straightforward. There are going to be 4 decision variables. I'm going to call them G1, G2, G3, and G4. Okay, where G1 is the amount of grain 1. I don't know why I'm doing that, but why not? So G1 is this is where you have to be very careful as how we define our decision variables. And the reason for that is pretty straightforward. So the decision variables, you can define the decision variables in 2 distinct ways here, and that sort of shapes how everything turns out. Now, if you look at the data, you want to make an 8-ounce packet of the raw grain. So you want to make 8-ounce packets and sell them as 8-ounce packets. But all the data is given. So the vitamin C per in the grain, the protein and iron, even the cost of grain, everything is given in pounds. So you have 2 options here. You can either solve the whole problem in ounces, or you can solve the whole problem in pounds. Now I'm going to do pounds because everything in this table, everything here is in pounds. The only thing in ounces is the packet, the weight of the packet itself. That's why I'm going to do it in pounds. But you can obviously do everything in ounces. You'll end up with the same answer. It's not going to be any different. But I'm going to do everything in pounds. So I'm going to say that G1 is the pounds of grain 1 in the mixture. Now you have to realize that the total mixture is 8 ounces, which is half a pound. So because the total mixture is only 8 ounces, what's going on? Because the mixture is only 8 ounces, the sum of each of these G1, G2, G3, G4, they're all going to be very small numbers because they have to add up to half an ounce, right? So half a pound. I'm sorry, they're going to add up to half a pound. So don't understand why this keeps happening. Okay. So pounds of grain 1, pounds of grain 3, pounds of grain 4. So these are the four decision variables. Our objective is to minimize the total cost of the mixture, obviously. So the total cost numbers are given here. Let's look at the cost numbers. The cost numbers at 75 cents per pound of G1. So because we did pounds, we can directly use the numbers. If you're doing ounces, you write it, obviously, divide the whole thing by 16 plus 80 cents times G3 plus 70 cents times G4. That's the total cost of the mixture, and that's what we are minimizing. When you're doing cost, it's always minimization, obviously, and we're going to be maximizing the cost. Okay. Right, next are the constraints. Let's begin with the constraints. So I have four constraints here. The first constraint obviously is that the sum of all of these variables has to add up to half an ounce. The total weight of the packet is half an ounce. So you get G1 plus G2 plus G3 plus G4 is equal to half an ounce. So half a pound. I keep saying half an ounce. It's half a pound. It's 8 ounces, right? So that's the total weight of the mixture. Next is the amount of vitamin C. So you need, the constraint says that you need at least 6 units of vitamin C, 5 units of protein, and 5 units of iron. So the total amount of vitamin C in the mixture is going to be based upon the number of units in pounds. So it's going to be 9 times G1 plus, what I'm not getting, 9 times G1, 16 times G2, because there are 9 units of vitamin C in every pound of grain 1, and G1 is the pounds of grain 1. So let's say that G1 is 0.1, means a tenth of a pound. Then there'll be 0.9 units of vitamin C in it. So 16 times G2 plus 8 times G3 plus 10 times G4. So this is the total amount of iron in the mixture, 9, 16, 8, and 10. Total amount of iron in the mixture, sorry, vitamin C in the mixture, and this has to be at least 6 units. Similarly, next we come to protein. It's 12 times G1 plus 10 times G2 plus 10 times G3 plus 8 times G4 is greater than or equal to 5, right? There are 5 units, 6 units of iron, 5 units of protein, and 5 units, sorry, 6 units of vitamin C, 5 units of protein, and 5 units of iron. And there's a minimum. So next is the iron. There's no iron in grain 1, so it's just going to be 14 times G2 plus 15 times G3 plus 7 times G4. This has to be greater than or equal to 5, right? And that is it. We have 8-ounce packet, and we have the nutritional values in, and that's it. So those are our constraints. Now here we obviously need non-negativity, but we don't need integer constraints, because definitely the variables are going to be not integers. So let's put this in solver. Okay, I'm going to call this blending. Okay, there are 4 decision variables here. Let me make the font bigger, it's easier to see. So you got grain 1, G2, G3, and G4. And of course, left hand side and right hand side. Right. Okay. Now let's begin with the decision variables. It's G1, G2, G3, G4. Color them as usual. So these are my oops. So these are my decision variables. Then there's the objective. So the objective is it's 75 cents. Cost 75 cents to buy 1 pound of grain 1. Then 90 cents for grain 2, 80 cents for grain 3, and 70 cents for grain 4. Right? And then of course the constraint. The first one is the weight. Total weight constraint. So the sum of all the grains that you put in, all of this has to equal half an ounce. Now this is where you have a couple of options. Half a pound. This way you have a couple of options. Instead of saying equal to, you can say greater than or equal to. You can potentially say that you could potentially put more than half an ounce. That's half a pound. That is fine. But because this is a cost minimization problem, you're going to get it to be exactly 0.5. You're not going to do more than what is necessary. Right? But you could leave that option open in case you want it. Right? Next is the minimum of vitamin C. Then you got minimum of protein, and then minimum of iron. Right? So we got the numbers here. Let me put it right there. So here you can either put a 0 into into grain 1 because there's no iron in grain 1. You can just leave it blank like we've been doing before. Either way will work. This is greater than or equal to. It's all greater than or equal to. Right? And you need a minimum of 6 units of vitamin C, 5 units of protein, and 5 units of iron. Right? That's it. So once that, we can write the sum product formula of the objective coefficients, comma, the decision variables, which are going to be absolute references. There you go. So these are this is the setup. Let's put this into solver and solve it. Right. Let's begin. So the objective is right here. You're minimizing the total cost. So that's the objective, the total cost. By changing the values in the cells. These are my decision variables, B2 to E2, right? And then I'm going to add 2 constraints. One is the equal to constraint, saying that this sum has to equal this number. So F6 is equal to H6, F6 is equal to H6. And add F7 through F10, F9 have to be greater than or equal to H7 through H9. So F7 to F9 is greater than H7 to H9. These three are all greater than or equal to constraints. I clustered them together so I can write them all at once. Then I'm going to click on solve. And remember, these are all in pounds. So if you want the answer in ounces, you can just multiply all these numbers by 16. You'll get your answer in ounces. So these are all in pounds. So if you want in ounces, you can just say this times 16. And let me reduce the number of decimal places. So I'm not rounding it. I'm just showing only 2 decimal places. So this is the decision variables in ounces. Right. So you're saying that to make your 8-ounce packet, you add 1.59 ounces of grain 1, 3.4 ounces of grain 2, 1.41 ounces of grain 3, and 1.59 ounces of grain 4. Now, obviously, these 4 will add up to 4. Right. So they add up to 4. That's what you have. How's that? Right, they add up to 5, not 4. They add up to 5. They add to, right, so they add up to 8, not 4. I keep thinking 4. No, they add up to 8. So add up to 8 ounces, which is 16, half a pound, right? So they add up to 8 ounces, and that's how you know that this is what the answer is, right? And there you go. Okay, that's a solution, right? Okay, take care.